Section 4.4, rational functions. Up until this point, we have been talking about polynomial functions. You remember, with polynomial functions or smooth functions, you can draw them without lifting your pencil. Not the same thing with rational functions. A rational function, similar to a rational number. Anytime you see the word rational, I want you thinking fraction. So it says the rational function is the quotient of two polynomial functions. So you got a polynomial function divided by a polynomial function. Here are some examples of rational functions, and you see f of x, g of x, and h of x there. Three rational functions. Just anytime you have a fraction to where you have, well, you got to be careful. Anytime you have a fraction, you have x stuff on bottom. That's a rational function. The domain of a rational function, probably remember this from a few lessons back. Domain of a rational function, remember that division by 0 is undefined, therefore anything that makes the bottom of the function 0 is not a member of the domain. So looking back up here, f of x, can you tell me how many different things are not in the domain there? Is 0. 0 is fine. There's two different things that's not in the domain. Can you tell me what the two things are? Plus and minus the square root of 3. If you set the bottom equal to 0 and solve it, move the 3 over, take the square root of both sides. Positive square root and the negative square root of 3 is not in the domain. G of x, what's not in the domain there? 0, and can anybody do the third one in their head and tell me what's not in that domain? Negative 1 and negative 2, actually, because you got x plus 1 and x plus 2 is what that factors into. So therefore, that's how you find the domain. Example 1, that's all you're doing. Example 1 says find the domain of each rational function. A part. Again, you can do it one of two ways. You can say what the domain is, or you can just tell what's not in the domain. Easier to tell what's not in the domain. On A part, what two things can x not be? 0 and 6. Okay, so if you wanted to write that out, anything from negative infinity to 0, not including 0, from 0 to 6, not including either one, from 6 to infinity, you can write it like that, but the easy way to write it, x is not 0, x is not 6. The second one, all you got to do is factor, and this is, I think, that same one that we saw up top. Yeah, it factors into x and x, plus 2 and plus 1, so x can't be negative 2 and x can't be negative 1, because that makes the bottom 0. Any questions? I'm going faster through that because hopefully that's stuff that we've done this year, so hopefully you remember it. Negative, because if you positive 2 is fine, because if you plug a positive 2 into that, you get 4 times 3, which is 12, no problem there. But negative 2, you get 0 times negative 1, which gives you 0. Can't have a 0 on the bottom. Intercepts of rational functions do the same thing, and we've actually done the second part also. Y-intercepts, plug in 0 for x. X-intercepts says it has to make the numerator 0 but can't make the denominator 0. And let me show you what I mean by that on this next example. Example 2 says find the intercepts of the following function. Let me write this down and work it out. G of x equals x squared minus 2x minus 3 divided by x minus 3. So if we want to find the x-intercepts, well, let's do the y-intercept first. It's easier. How do you find a y-intercept? Plug in 0 for x. So you get, pretty much what you're doing is g of 0 is your y-intercept. So can anybody do that in your head? Pretty much anything that's an x, negative 3 over negative 3, which is a positive 1, is your y-intercept. Because anything that's x is going to go to 0. 0 minus 0 minus 3 over 0 minus 3, which is negative 3 over 3, negative 3, which is positive 1. To find your x-intercept, and we have done this before this year, you set y equal to 0. So erase g of x and set the whole thing equal to 0. Do you remember how to solve those? How do you divide something to give you 0? X over 3 equals 0. What does x have to be? 0. Because anything divided by whatever, if it's going to give you a 0, then obviously the top must be 0. So to solve these, all you have to do is say, okay, what makes the top 0? So x squared minus 2x minus 3 is 0. Set the top equal to 0, solve it, factor x negative 3, positive 1, so x is negative 1 and positive 3. There's a problem there. Can anybody tell me what the problem is? X cannot be positive 3. Look at your domain. X can't be 3, so mark it out. Your x-intercept is negative 1. Any questions? The bottom, if it's equal to 3, it's undefined. Okay, next up, talking about vertical asymptotes. You might remember this from last year. Rational functions aren't continuous. Okay, you can't draw it by not lifting your pencil. It says there are breaks where the function is not defined, or is undefined. The function will have no sharp corners, though. Vertical asymptotes. And again, hopefully you remember this from Algebra 2. Vertical asymptotes, and vertical means up and down. Vertical asymptotes occur when you have a factor of the bottom that is not also a factor of the top. What I mean by that, if you have f of x equals x plus 2 times x plus 3 over x plus 2 times x plus 1. Okay, first off, tell me again, what's not in the domain? X cannot equal what and what? Negative 2 and negative 1. So what actually happens at negative 2 and negative 1 is one of two different things. You either have a vertical asymptote there or you have a hole there. One or the other. What a vertical asymptote is this vertical line that's not actually part of your graph that your graph gets closer and closer to, but it doesn't actually ever touch it. So it's not defined at that asymptote. So what happens is when you have a factor of the bottom that's not a factor of the top, notice x plus 2. Is x plus 2 also on the top? Yes, that's not a vertical asymptote. You have a vertical asymptote at x equals negative 1. Vertical asymptote there. So this graph, if this is the line x equals negative 1, that's kind of like what this graph would look like. So vertical asymptotes appear where you have something that's a factor of the bottom that's not also a factor of the top. Any questions? I'm going to skip this big little concept for now and go down here. I don't know why I threw it in right there. It says the graph around a vertical asymptote could look like any of these following three pictures. You've got the vertical asymptote here. You can go down as you get closer. One could go up and the other side could go down, or they both could go up to positive infinity around that asymptote. Example 3 says, find the vertical asymptote of the following function and tell the behavior next to the asymptote, which is new this year. So you might want to watch that part. 3x minus 2 over x plus 3. F of x, we'll call it. Okay, first part, vertical asymptote, I'll just call it the VA. What is it? X equals negative 3. There's a line at negative 3. Okay, you've got a vertical asymptote at x equals negative 3. But I want to know, what does this graph do on the left side of it, and what does it do on the right side of it? Let me show you how to do that. Pull up my graphing calculator. Okay, to find out what it's doing on each side, just plug in something really close to negative 3. It's only undefined at negative 3. I can plug in negative 2.9, and I can plug in negative 3.1. And that should tell you, okay, what is my graph doing? Is it, because I told you it does one of three things. Either it goes up on one side and down on the other side, or it could go down on one side, up on the other side. They both could go up, or they both could go down. One of four things that it could do. So what I'm going to do is I'm going to plug in things really close to negative 3 into this equation. So, second quit. If I plug in negative 2.9, am I on the right or left side? Right side, because here's 0 over here. So negative 2.9 would be somewhere right in here. And then I'll plug in negative 3.1 on the other side, and just to see what my graph's going to do. So plug in negative 2.9, I've got 3 times, I'll just do it all in one. 3 times negative 2.9 minus 2 divided by negative 2.9 plus 3. You get negative 107. So think about that. At negative 2.9, you're at negative 107. Can you tell what your graph's doing? It's going down on that side. So and you could write it like this: As x approaches, here's new notation. You've never seen this before. As x approaches -3 from the right side, you could put a plus sign up there because it's approaching it from the positive side. Y approaches -infinity. Makes sense? And then as x approaches 3 or -3 from the left side is what we're going to do next. Y approaches, I don't know. So plug in -3.1 to find out what it does on that side. So you can go back and do second entry, and then anywhere you have -2.9, put -3.1. You think it's going to go down? 3.1, positive 113. So you're way up here at -3.1, so it's doing something like this. So as x approaches -3 from the left side, y approaches positive infinity. Any questions? We're learning ways to graph without having to graph. Learning what a graph's going to look like without even having to graph it in the first place. What I normally do is you'll get to where you can kind of plug them in your head. You can tell, okay, is it going to be, because really all you're interested in is it going to be a positive value or is it going to be a negative value? And you can say, okay, when I plug in -2.9, obviously I have a negative on top. Does that make sense? And on bottom I have a -2.9 plus 1, which is a positive, so it's going to go to a negative. Since it's a negative, then it's going to go down. When you plug in -3.1, you've got a negative over a negative, which is a positive, so it's going to go up. That's the quicker way of doing it. Just worrying about the signs.